Thanks, Srikanth, and thanks to Wi-Fi KS for giving me this opportunity. And thanks to Praveen. Uh, I'm happy to know that there's a tree with my name on it somewhere. It's good to hear about that as well. So today's talk is going to be on home Wi-Fi networks. It's going to focus on performance of home Wi-Fi networks and hopefully some insights on how to provision home Wi-Fi networks based on some experimental study. This was a work done in the Department of Electrical Engineering, and my students Amrita and Divya did the major part of the work, and I'm just presenting it here. Next slide, please. I don't need to motivate Wi-Fi networks or provisioning home Wi-Fi networks. However, I'll quickly tell one or two important points that are relevant here. Of course, Wi-Fi usage at homes is increasing, and with the COVID pandemic, many of us are working from home, and it becomes more important to understand whether our Wi-Fi network is operating efficiently, optimally, etc. These days, at least in the last few years, we have very good broadband connections, wired broadband connections. Hundreds, even 300 Mbps is now very common. With increased broadband connectivity speeds, the customers are also demanding a better quality of experience, and not just the wired, but also through the wireless connection. They are demanding ubiquitous coverage. They are demanding guaranteed throughput in the entire home. Okay, and we all know that Wi-Fi links can become a bottleneck if we do not manage the links efficiently. So understanding home Wi-Fi networks and important aspects that we need to care about becomes important. While there's a lot of reported work, the challenges in the Indian context, specifically the construction material, the size of homes, etc., are not well understood or reported. So that's where our work fits in. Next slide, please. So I'm going to present my talk in this order. I'll quickly explain what is the problem statement, and then I will tell the experiment and measurement methodology that we use to appreciate Wi-Fi performance. Then I'll present our results on coverage and throughput, and then I'll make some recommendations for Wi-Fi deployments based on the inferences, and finally I'll comment on the ongoing work. Next slide, please. So what are we actually going to study? We are going to study two things. One is Wi-Fi coverage in terms of signal quality, and Wi-Fi performance, largely throughput, in typical Indian homes. That's the objective. Okay. More specifically, we are going to actually characterize Wi-Fi link performance, and later I'll interpret how Wi-Fi link performance can be extrapolated to appreciate Wi-Fi network performance. And we are going to characterize link performance as a function of radio configuration, as a function of device capabilities, as a function of the size of the home, etc., so that we get a quick appreciation of Wi-Fi performance based on some basic parameters about the home. Based on the study, we are hoping to develop or appreciate what are good deployment strategies in terms of where to place the APs, what is the radio configuration like, what management is necessary, etc. And I'll give some illustrative suggestions if we are seeking whole home coverage with, say, 100 Mbps guaranteed throughput. This is the two problems that I'm going to discuss in this presentation. Next slide, please. Okay. We have heard a lot of discussions, and many of us already know these things, but nevertheless, I would like to point out that to understand home Wi-Fi performance, we have to understand two important things. One is performance of a single Wi-Fi link, and the other is performance of a network. If you look at performance of a single link, it depends on a variety of factors. I'm just listing few of them, important ones. It depends on the radio standard. It depends on the capabilities, how many antennas, for example, the device has. It depends on the configuration that you choose, bandwidth, etc., of both the AP and the client. Then it depends on the wireless channel quality. For example, how far is the client away from the AP? It depends on the interference in the environment. It depends on mobility in the environment or the device itself, etc. In addition, we all know that it also depends on the device quality. the AP as well as the client quality, the hardware, the processors, etc., the software, and also the RF design and so on. So the link performance itself depends on a variety of factors. In addition, when you look at performance of a Wi-Fi network, then things like the number of associated stations to the AP, OBS's interference, the nature of application, the traffic, the transport protocol, RRM support, power control, channel selection, user association, scheduling, etc. All these matter. And of course, the internet bandwidth, that also is a crucial factor. Okay, so it's a lot of aspects to look at before we understand the home Wi-Fi networks. Next slide, please. However, I would like to kind of tell that ensuring Wi-Fi link quality is paramount. And I mean, if the link quality is poor, obviously your network performance is going to be poor. So the first thing is that we have to ensure Wi-Fi link quality. And then I will possibly convince later that, or at least tell you now and possibly convince later during the question and answer session that if you have contention in your BSS, and if you want to give certain priorities, if you want to implement certain notions of fairness, you can possibly manage them through AP. There have been many bandwidth manager solutions that we all know, including one from Professor Anurag Kumar's group. From IIT. Contention in a BSS, etc., can be managed through software, and OBS's interference. In some cases, at least in the 5 GHz band, the OBS's interference can be managed effectively using RRM. I'm talking about the home Wi-Fi network, not the other hotspots or stadiums, etc. So this, I'll comment on it later, but so my conclusion is like, if you can take care of the Wi-Fi link, then most likely you can take care of other things easily in this setup. And for Wi-Fi link performance, we have decided to actually understand the link performance through experiments. So rather than analytical or simulation-based models, we have decided that why don't we characterize the performance through experiments? And we decided to use commercially available access points and client devices. And we decided to make the measurements in real homes, in real environments, so that we appreciate, we can sample what is it like. Okay. And we use mobile phones for clients, it's the most common device that's being used. And the performance that we get with mobile phones is also a good indicator of the performance that you can get for other devices such as laptops or televisions. So what are we hoping to study? We are hoping to study two things. One is coverage and the other is throughput. We are going to study coverage or measure coverage in terms of beacon RSSI, average beacon RSSI, and throughput in terms of TCP or UDP throughput. And we are going to study coverage and throughput as a function of important parameters, which is the radio configuration, the bands that we are going to operate. And we are considering, we did this measurements a year back, 2 years back. So we used 11N for 2.4 GHz band and 11AC for 5 GHz band. And then we are going to compare as a function of radio capabilities, 1x1 and 2x2 client devices. We were using mobile phones, so we restricted to these two configurations. And we sampled homes of different sizes, 1, 2, 3, 4 BHK, as well as duplex homes across 2 states. Finally, we used TCP and UDP traffic. We considered both downlink and uplink traffic. And all the traffic was routed from a local server to ensure that Wi-Fi is the bottleneck and not the internet. So with this setup, we studied the Wi-Fi link performance, and I'm going to actually present the results based on this study. Next slide, please. Once again, to kind of bring to your notice what the experiment setup is like. So we had an AP which was placed in the usual or preferred location at the home. Wherever the AP was originally there, we kept the AP, our AP there. And then we had a wired connection between the server and the AP rather than connecting the AP to the internet, so that Wi-Fi is indeed the bottleneck, so that we can actually study what is the expected performance in a Wi-Fi setup. And then we had a mobile phone, and the mobile phone was actually held in hand like a typical usage. And the mobile phone was also subjected to limited mobility, like in typical environment. A wireless sniffer was actually used to measure the channel quality as well as to measure the monitor the packets over the air, rather than measuring the values from the client. And if there is a later, if needed, I can explain why it was. We used a MacBook Pro for the sniffer. and we conducted all our experiments using IPOF3. Next slide, please. This is typically the setup like. So we have here I'm illustrating a floor plan of a 2 BHK. The red box indicates the location of the AP, and the cyan boxes indicate the location, the various locations where we did measurements. Like I said, we made measurements in 25 homes, 5 each of 1 BHK, 2 BHK, 3 BHK, 4 BHK, and duplex homes. And in each home, we roughly made 8 to 10 measurements. That's approximately 200 plus sites. And in each site, we made 8 measurements, or we conducted 8 experiments where the configurations are 2.4 or 5 gigahertz, 1x1 client device or 2x2 client device, downlink or uplink. So that's roughly 8 measurements. So in all, we had 1,600 plus experiments. And in addition to measurements of measurements from these experiments, we also recorded the floor plan, like I'm illustrating it here. We also recorded the distance between the AP and the client devices, the average distance, and also the number of floors and walls between the AP and the site of measurement. So this is roughly what we did in all these locations. Once again, these were at real homes, and we did not interrupt the activity in the real home when we were conducting the experiments. So there was a lot of uncertainty during the measurements, and most of the measurements were done during the daytime. Next slide, please. A quick sheet on the important hardware specifications and software specifications. In 2.4 gigahertz band, we used 20 megahertz bandwidth, and 5 gigahertz band, we used 80 megahertz bandwidth. So just wanted to highlight that. Next slide, please. And most of our experiments were for 30 seconds. So now let me present our results. I'm here presenting the coverage measured in terms of beacon RSSI, and I'm actually presenting the CDF, cumulative distribution function, of the coverage signal quality for 2.4 gigahertz band and 5 gigahertz band. On the left-hand side, I'm plotting the CDF for 2.4 gigahertz band and for the different home types, 1 BHK, 2 BHK, and so on. You can see that the coverage is typically between minus 30 dBm to minus 70 dBm. And of course, the signal quality is better for small homes, while it is actually poorer for large homes, as expected. In 5 gigahertz, the signal quality is actually minus 40 dBm to minus 80, 85 dBm. You see that the average RSSI in 5 gigahertz is actually 10 dB less in comparison with 2.4 gigahertz. And that's typically how we observed through all of our measurements. The signal quality in 5 gigahertz was typically 10 dB less in comparison with the signal quality in 2.4 gigahertz in each location. Okay. Next slide, please. I'm presenting the same plot, but now rather than as a function of the type of home, I'm presenting it as a function of how far the measurement site was from the AP. Was it in the same room as the AP, then I call it as 0 wall. If it is 1 wall away from the AP, I call it as 1 wall. And if it's 2 walls away, I call it as 2 walls. So you notice in the left-hand side image for 2.4 gigahertz band, if you are in the same room as the AP, your signal quality is pretty good. It's between minus 30 to minus 45 dBm. However, if you are 2 walls away, it's between minus 40 to minus 70, minus 75 dBm. So the signal quality gets poor as you move 1 wall away. There's at least a 10 dB loss. And when I say wall, this could be a wall. This could be wall adorned with some, say, television, some almiras, etc. So it's a kind of a, it's not a clean wall. So there can be many things that affect the actual signal strength. On the right-hand side, 5 gigahertz, for the 5 gigahertz band, you can see that the gap between the 3 curves is actually quite wide. You start with minus 40 to minus 55, and then when you go 1 wall away, you are between minus 50 to minus 70, and when you are 2 walls away, it's already starting at minus 60, minus 65 to minus 80, minus 85. So clearly, when you are 2 walls away in a 5 gigahertz band, your signal quality is extremely poor, minus 70, minus 75 dBm, and I'll mean what it implies for performance in a minute. Next slide, please. Here I'm reporting the throughput in 2.4 gigahertz band for 1x1 client devices. The throughput is between, I'm talking about the TCP throughput. It's between 30 Mbps to 60 Mbps. When you're 2 walls away, there is some hit, 10 Mbps hit, but more or less it's fine. On the right hand side, I'm plotting the throughput versus the average RSSI. You see that when the signal quality is good, you get around 60 Mbps, 55, 60 Mbps, and when you are actually away, there is some variability, but on an average, you are getting around 30 Mbps. So I would say that with a 1x1 client device, you can expect throughput of 30 to 60 Mbps in 2.4 gigahertz band. Next slide, please. I'm reporting the results for 2x2 client devices, and here it's now between 40 Mbps to 100 Mbps. That's an improvement because of the multiple spatial stream support to spatial stream support. And when I see the performance of throughput versus RSSI, it's again it's in the best locations it's around 80, 90, and 100 Mbps, and it can go up to 30, 40 Mbps. So it's still reasonable in many counts. So 2.4 gigahertz, when there is little interference, then it looks like you can get throughputs of the range 40 to 100 Mbps. Next slide, please. So here I'm reporting the performance for 5 gigahertz 1x1 client device, and I want you to appreciate the left side image. Here I'm plotting the CDF of throughput, TCP throughput, as a function of walls. When you are in the same room as the AP, your throughput can actually be between 200 Mbps and 300 Mbps. That's quite good. However, when you are 1 wall away, there's a lot of variability. It can go all the way to 0, but nevertheless, like 50 Mbps to say 200 Mbps. But when you are 2 walls away, you see that there is a sharp dip in the performance, and most of the time you are getting throughputs less than 100 Mbps, and 40% of the time it's actually less than 50, 30 Mbps, and 20% of the time it's actually less than 20 Mbps. The right-hand side image actually gives you the data in a different perspective. Throughput versus RSSI, you see that if the signal strength is below minus 70 dBm, you see that you can actually get 0 throughputs in many places, and the signal throughput performance can be arbitrarily low. This we have seen consistently. With 5 gigahertz, there is a rapid deterioration of throughput as RSSI decreases. And because the signal quality can be poor beyond 2 walls, throughput is actually poorer in large homes. And there's a lot of variability once the signal quality decreases. This we did not notice in 2.4 gigahertz when there was always a floor like 30 Mbps, 40 Mbps, but in 5 gigahertz, when the signal quality is poor, which is often the case, the throughput is very low. And we see a clear impact of wall on the performance in the first figure. Next slide, please. I'm reporting the performance here for 2x2 client device. When you are in the same room as the AP, the 0 wall case, the throughput is between 300 Mbps to 500 Mbps. That's fantastic. However, when you're 2 walls away, the 80% of the time your throughput is less than 100 Mbps. And once again, 20% of the time it's very less, it's less than 20 Mbps. And in many cases, it's even 0. In many cases, we noticed that with 5 gigahertz, when the signal quality is poor, we were not able to connect, or we were not able to actually get any throughput. This is, once again, I'm reporting it again. The 5 gigahertz, in 5 gigahertz, performance deteriorates rapidly once the RSSI is less than minus 70 dBm. And there's a lot of if you're in the same room or if you're 1 wall away, things are very good, but 2 walls away, things are really bad. Okay, next slide, please. Here I'm reporting some additional results. We tried to understand the performance of downlink versus uplink. We did not really notice a lot of difference. In fact, in many cases, we noticed that the uplink performance was good. But nevertheless, the difference was not too much. And on the right-hand side, I'm plotting the throughput in 2.4 gigahertz versus 5 gigahertz. When the signal strength is good, the 5 gigahertz actually reported a very high throughput simply because we had 80 megahertz bandwidth in comparison to the 2.4 gigahertz band. However, when the signal quality is poor, the 2.4 gigahertz band at least gave us a 10-20 Mbps throughput, while the 5 gigahertz band in the same location would often give us 0 throughput or quite a variable amount of performance. So this is what we noted. Next slide, please. While the previous results that I reported were from real home experiments, there was a lot of variability. We decided to reduce the variability, and we conducted some experiments, the same set of experiments, but in a static environment where the mobile phone was in a static location, the No one was inside the home. Not even a fan was operating. So in a very controlled setup, we conducted these experiments and we got actually very similar performances. There was a shift in the curve, obviously, because the variability in the channel quality is now reduced. However, the trends were very similar. When the signal quality is poor, when it's -70, -105 dBm or below, then your performance is actually poor in 5 GHz band. So the same results we noticed, and we also noticed that the TCP throughput was a very good indicator of performance of the average phi rates. There was a good correlation between throughput and rate. So we believe that TCP throughput can be used as a measure of performance of Wi-Fi links. Next slide, please. So let me now try to conclude our observations. What did we observe in 2.4 GHz band? Coverage is actually adequate even in large homes. We got really -70, -105 was the worst that happened. We got a really good performance between 30 Mbps to 60 or 40 to 100 Mbps. So on an average, I would say 50 Mbps was easily achieved. The challenge is that we have limited bandwidth options. If you're in a standalone home, you can improve the bandwidth to 40 megahertz and you can actually get a better performance. But otherwise, due to co-channel interference, you'll be in serious trouble, especially in cities. In apartments, there'll be serious co-channel interference. Remember the propagation losses in the 2.4 gigahertz band, the signal propagates to farther distances. So there is going to be a lot of co-channel interference. So that restricts our bandwidth options also. In 5 gigahertz, we notice that the coverage is poor beyond 2 walls. That necessitates us to look at options such as mesh routers or multi-AP architectures. However, when the signal strength is -65 dBm or above, we actually got good throughput. And I'm considering a -65 dBm just so that, to account for variability in terms of channel quality or interference, just in case. In 5 gigahertz band, we have excellent channel and bandwidth options. And co-channel interference may not be a serious concern. As we observed, beyond 2 volts, the signal strength is quite weak. So we expect that the interference strength is also going to be quite weak in 5 gigahertz band. So in 5 gigahertz band, I believe that with the excellent channel and bandwidth options and that interference is kind of weak in this band, I think we have a good set of solutions available for the kind of requirements that we have. Next slide, please. So if I were to make a recommendation with say 100 Mbps as kind of some number that we are targeting, I would say that we should look at 5 gigahertz band and 80 megahertz bandwidth. Due to some reasons, if 80 megahertz is not easy, then we can even go for 40 megahertz and still be happy about it. MIMO support, yes. If we go for 2x2, then even with the 40 megahertz bandwidth, we can guarantee ourselves fantastic throughput performance. One recommendation with respect to placement is that we should seek a coverage of -65 dBm or higher at each location. So roughly what it means that all the locations must be at most 1 wall away from the AP, and important places where you sit and operate should not be in a shadow. There should be a reasonable view to the AP, except for at best 1 wall or so. That also implies that when you have a large home, you would definitely need a mesh or a multi-AP architecture. So these are the basic recommendations that are needed for 100 Mbps coverage. In addition, of course, we need intelligence at the access points. We need to ensure that we have good power control to mitigate poor coverage just in case. We need to have good channel and bandwidth selection strategies to avoid interference. Remember, we have enough channel and bandwidth, so it would be nice if we can avoid interference, especially in the home environment. And of course, when you have a mesh or a multi-AP architecture, we need good user association strategies so that you are always connected to the best AP. In addition, bandwidth manager at the AP can help isolate or manage your traffic so that the important traffic, your important traffic can be given preference, statistical or deterministic priority compared to the other traffic. So this is my recommendation for home Wi-Fi networks. Next slide, please. So most of what I presented is, this brings me to the conclusion of today's talk. Most of what I presented is published in the paper titled Wi-Fi Coverage in Indian Homes. It was published in the Proceedings of CompsNet 2021. Currently, we are looking at performance evaluation of a home Wi-Fi network. Remember, I studied the Wi-Fi link performance through experiments, and I kind of made a decision for home Wi-Fi networks, assuming that I can actually do RRM. To kind of complete the study, we are now conducting the performance evaluation of a home Wi-Fi network, and now we are actually doing it through a network simulator, where a lot of data from the experiments, channel evolution, and other things, that the rate adaptation algorithm and such ideas, we are actually putting into the network simulator, and we are trying to make a network performance evaluation involving multiple clients, OBS's interference, realistic traffic, etc. The goal is to develop a recommendation engine for home Wi-Fi networks, which would recommend how many APs you would need, what is the placement, what is the configuration, what are the RRM strategies required, etc. And we are hoping that this would add to the existing knowledge we already have for site planning and so on. Next slide, please. I would like to thank Qualcomm, Arista Networks, Cubocom, and NanoCell Networks for their grants, technical support, and help. And without that, this would have most likely never happened. Yeah. Thank you. Next slide, please. Thank you. I can take questions now if there is some time.
Thanks, Venkatesh. We do have a couple of questions at least. In fact, more than a couple. Chetan's question is, was any test done with multiple devices? It would be interesting to see the graphs of device throughputs with good RSSI when there are other devices with poor RSSI latched onto the same access point.
This is a problem that can be managed by a good bandwidth manager or a scheduler of the AP. If there are multiple clients, of course, the uplink traffic, there can be some problem, but I believe solutions, there are solutions which can actually handle traffic even in the uplink direction. For the downlink direction, the scheduler of the AP can trivially manage these things. So I believe that with a software solution, we can isolate the traffic of the multiple clients, and thereby this may not be a serious issue. This is hypothetical. I kind of know that we can do it to a reasonable extent, but this is my belief. So we did not conduct multiple client experiments due to the reason that some of the clients can actually drag the performance. But since this situation could be avoided, we did not do it.
Thank you. So Sohail has a couple of questions. Would like to know the TX power used on the AP for testing. And the additional question is also would be good to know using fork plan, which location was considered as a 2-wall away observation point?
The power that we used, so we did not actually have the exact power that was transmitted, but we kept the setting as high in a typical commercial AP. A 2-wall away is it's like a line of sight 2-wall away. So if there is an AP on one room, and if I draw a line between the AP and the site of measurement, if it crosses 2 walls, then I would call it as 2 walls. That's typically how.
I just brought the picture up. Would you like to use that?
In this case, possibly I don't see any 2 walls.
Okay.
Yeah.
Sure. Okay, I think we have one more question.
This is kind of this is a 2 BHK illustration. We went all the way up to 4 BHK and duplex homes, where we saw a lot of 2 walls.
Okay. Arjun has a question. Any study on near loss condition or refracted signal and impact on throughput?
We did not make any specific measurements of that nature. In fact, these measurements were, like I told you, this was the mobile phones were held in hand. So the human body created a shadow. We were moving around both. We were walking as well as sometimes we were actually moving around while sitting. There was a lot of variability, so we didn't do those specific measurements. However, we did independent experiments where we noticed signals propagating through diffraction and so on. And they gave some interesting results, but not to a conclusive thing. One thing is like we noticed that keeping the doors open helped us get a better performance. Sitting in the keeping the sitting in the direction of the wave propagation would help us get a better performance, like avoiding shadow due to body, etc. So, but not a conclusive experiments or data.
Thank you, Venkatesh.